This presentation will discuss confidence intervals, and then we'll move into considerations for conducting a correlational or linear regression analysis. Confidence intervals are a range of possible values that are likely to capture an unknown parameter given a certain degree of probability or confidence. Confidence intervals give us a range of possible values and an estimate of the precision for our parameter value. Hypothesis tests tell us how confident we are in drawing conclusions about the population parameter for our sample. The essence of this method is to compare the hypothesized value to the confidence interval. If the hypothesized value falls within the interval, we fail to reject the null hypothesis. If the hypothesized value falls outside the interval, we reject the null hypothesis. We remember that a null hypothesis is a form of a hypothesis that is deemed true until proven wrong based on experimental data, also known as the status quo or known accepted fact. It states that there is no statistical significance between two variables and is usually what we are looking to disprove. The lower and upper limit between which the true values of the population lie are the confidence interval. It determines the level of uncertainty in sample data. Here you see a normal distributed curve. The confidence interval says that 95% there's a 95% chance that your population mean will fall between 2.92 and 5.62, where you see as the lower limit and the upper limit, with the mean being 4.27. You'll frequently use confidence intervals to bound the sample mean and standard deviation parameters, but you can also create them for regression coefficients, proportions, rates of occurrence, and the difference between populations. Statisticians use confidence intervals to measure the uncertainty in a sample variable. For instance, a researcher may randomly select different samples from the same population and compute a confidence interval for each sample to determine how well it represents the actual value of the population variable. The resulting data sets are all different, with some intervals included and others not including the true population parameter. There are statistical assumptions that need to be conducted. The confidence interval of the mean of a measurement variable is commonly estimated on the assumption that the statistic follows a normal distribution and that the variance is therefore independent of the mean. This is known as a normal approximation confidence interval. Providing the distribution is not too skewed, central limit theorem means this assumption should be valid if your sample size is large. If the distribution is only moderately skewed, sample sizes of greater than 30 should be sufficient. The assumption will not be valid for small samples from a skewed distribution. For a large sample, where the number of participants are greater than 30, your estimate of the standard error will be relatively unbiased. Hence, you can say that the standard errors either side of the mean will enclose 95% of the means in that population. A common approximation is to give the arithmetic mean plus or minus twice the standard error of the mean. Confidence intervals are frequently reported in scientific literature and indicate how close research results are to reality, or how reliable they are based on statistical theory. The confidence interval uses the sample to estimate the interval of probable values of the population, the parameters of the population. For example, if a study is 95% reliable with a confidence interval of 47 to 53, that means if researchers did the same study over and over and over again with samples of the whole population, they would get results between 47 and 53, exactly 95% of the time. The reliability in this example refers to the consistency of the measurement or the ability to repeat it. Poor reliability can happen with a small population or if the event being studied does not happen often or at regular times. So a 95% confidence interval is the range that the similarly constructed intervals will contain the parameter being estimated. The sample mean will vary from sample to sample because of natural sampling variability. Here you see the confidence interval formula if you were looking to create this by hand. You would find the confidence interval level percent by taking 1 minus the alpha, where alpha is known as the significance level or accepted error, and alpha of 0.05 is typically a good level of accepted risk, but varies depending on the situation. So typically you'll see things like 95% confidence interval and a range of values. In other words, if the null hypothesized value falls within the confidence interval, then the p-value is always going to be larger than 5%. Conversely, if the null hypothesized value falls outside of our confidence interval, then the p-value is going to be less than 5%. Luckily, we are able to calculate this using SPSS. So you're going to take your data set, you're going to go from analyze to descriptive statistics and crosstabs. Once you hit OK, you're going to get to the crosstabs menu. Here you will pick the two things. I'm looking at Algebra 1 and math grades. You will notice here off to the far right that we have statistics, cells, and some other tabs. We are going to use statistics and cells. So you're going to first click on statistics. One thing to be very careful of, if you look at the diagram on the left, you want to ensure that nothing is checked with the exception of risk. So if you have any of those checked from previous analysis, uncheck them, check risk, and when you hit continue, it will take you back to this main menu. Then you are going to click on cells, the second button down on the right, and it will take you to this second image on the right. Here you want to ensure that only observed and row are checked. Again, if you have something else checked from a previous analysis, just you want observed and row. Again, you'll hit continue and then OK, and it will give you this output. What we are looking for here is under risk estimate. Here you see your 95% confidence interval with the lower and upper limits. Remember that if the upper and lower limits have the same sign, both positive or both negative, the distance is significantly different. And here we can reject our null hypothesis because both of the upper and lower are positive. In this article, the effects of speaking instruction via whole language approach, collaborative instructional design on pre-service teachers' speaking anxiety and speaking self-efficacy. This was a study that was done within the context of improving pre-service teachers' speaking abilities. Speaking is an interactive, meaning-making process that is critical for teachers at all levels to do well. The ability to speak correctly and properly can be improved by participating in speaking activities and using good speakers as an example. The data was analyzed using an ANOVA t-test and concluded with the findings that pre-service teachers that received collaborative speech instruction have decreased anxiety with public speaking. The authors identified that teaching speaking activities based on whole language collaborative instructional design had a decreasing effect on pre-service teachers' speaking anxiety. Confidence intervals could have been used in addition to the t-test to determine how well the t-test represented the whole population. It could also help to determine that the null hypothesis was false. In this case, the null hypothesis being that the instructional design sessions would not improve pre-service teachers' speaking efficacy. Some key takeaways on confidence intervals. A confidence interval in statistics is the range of lower and upper values within which true values of a population lie. The margin of error is the deviation between sample values and population outcome. And when the sample size is large, there are fewer chances of error, shrinking the standard error. Some article analysis using the article Investigation of the Effect of Augmented Reality Application on Preschool Children's Knowledge of Space used the Wilcoxon Signed Rank Test. This test is used to compare two related samples, matched samples, or to conduct a paired difference test of repeated measures on a single sample to assess whether their population mean ranks differ. This study was important because integrating science education into different activities that are in line with the developmental characteristics of children, especially during preschool, are critical. Augmented reality technology creates an enriched environment by imitating the real world through a variety of computer-generated activities that occur in a virtual environment. Applications made with traditional teaching methods were compared to the use of augmented reality technology in this study. The results of the analysis made with the Wilcoxon test of the scores obtained by the children in the experimental group from the questions developed before and after the application with the augmented reality cards was presented. There was a significant difference between the pre-test and post-test scores of the experimental group, where p was equal to 0.002. The authors identified that the mean ranks and sums of the different scores in the observed differences showed favorably in the post-tests. The authors concluded that the augmented reality application increased the knowledge of preschool children about space. The results were similar for the control group, where p was 0.003. The conclusion was drawn that applications made with 2D visuals increased the knowledge of preschool children about space. You can also do a Wilcoxon test using SPSS following these steps. Analyze non-parametric tests, legacy dialogues, and two related samples. Here I chose my two samples were the father's education and mother's education, and visualization test and visualization test 2. And again, when you click OK, the results are showed in the table to the right. Next, we're going to move into correlational and linear regression analysis. Correlational analysis is a statistical technique employed in measuring linear relationships between variables. A causal relationship between variables cannot be inferred using correlational analysis, regardless of the magnitude of the correlation observed. Linear regression analysis is commonly used for modeling the relationship between a single dependent variable, y, and one or more predictors. When we have one predictor, we call this simple linear regression. So what's the difference? Correlational analysis quantifies the strength of the linear relationship between a pair of variables, whereas linear regression analysis expresses the relationship in the form of an equation. A correlation is the measure of a relationship between two or more variables. A correlation is simply defined how well two separate variables go together. For a teacher, the two variables might be items such as correlating a successful homework assignment for students to their grades on a related assignment. Correlations also hold the distinction of being the statistics that is most likely to be misunderstood and misused in education. It is possible to correlate any item to any other item. Some correlations are silly, such as the correlation made between the relative abundance of clouds in the sky to a winning lottery ticket. Other correlations have a real value to teachers, such as the correlation between the amount of time that students study and student achievement. Sometimes correlations are useful, sometimes they are not, sometimes they are positive, and sometimes they are negative. In statistics, correlation refers to the fact that there is a link between various events. One of the tools to infer whether such a link exists is correlation analysis. Practical simplicity is undoubtedly one of its main advantages. Correlation is very important in the fields of psychology and education as a measure of relationship between test scores and other measures of performance. With the help of correlation, it is possible to have a correct idea of the working capacity of a person. Some examples. Is there a relationship between the number of parkas sold and the number of skiing accidents reported? Are smokers more or less likely to run marathons than non-smokers? Is there a relationship between life expectancy and the color of paint on a house's walls? It is important to keep in mind that correlational studies are looking for a relationship between two concepts. They are not trying to determine whether one variable causes another. This graph represents the linear relationship between the output variable, which is y, and the predicted variable, which is x. The blue line is referred to as the best fit straight line. Based on the given data points, we attempt to plot a line that fits the points the best. In simple terms, the best fit line is a line that fits the given scatter plot in the best way. A positive correlation between two events means that when the value of one item increases, then the value of the other item is likely to increase. An example of a positive correlation is the relationship between height and weight. Taller people generally weigh more than shorter people. However, since there are plenty of short people who weigh as much or more than tall people, the correlation cannot be described as strong. A strong positive correlation means that when the value of one item increases, the value of the other item also increases. An example of a strong positive correlation is the relationship between an increase in wealth and an increase in spending. A negative correlation describes an inverse relationship. In this case, when one event increases, the other decreases. For example, before the advent of safety devices in cars, a negative correlation existed between increasing car speed and the number of days without car accidents. In this case, the faster the cars were able to travel, the less the chance of an accident-free day. In correlational analysis, an example might be, a study might show that students who report reading more books score higher on end-of-year tests. This tells us two factors, reading more books and test scores, are related. It can even tell us how strongly the two factors are related. The primary objective of the study, a correlational study of teacher efficacy and culturally responsive teaching techniques in a southeastern urban school district, was to examine how teacher efficacy impacts culturally responsive teaching techniques, instructional strategies, student engagement, and classroom management. In addition, personal teacher efficacy and general teacher efficacy of high school teachers was examined. The teacher sense of efficacy scale was used to determine the dimensions of efficacy: instructional strategy, student engagement, and classroom management. Using SPSS, the authors used correlational analysis to determine the strength and direction of relationship between these things. Statistically significant relationships were uncovered between teacher efficacy, culturally responsive teaching, student engagement, instructional strategies, and classroom management. Linear regression analysis is used to predict the value of a variable based on the value of another variable. The variable you want to predict is called the dependent variable. The variable you are using to predict the other variable's value is called the independent variable. How do we calculate linear regression? You will see this formula, y equals mx plus b, that most of us remember from our algebra days. This is the slope intercept formula that is used to calculate, where y is the response or the dependent variable, x is the predictor or independent variable, m is the estimated slope, and b is the estimated intercept. Some educational research examples. How do parents and siblings affect the school outcome of a child? How does school climate and student socioeconomic composition impact average school achievement? What are the factors that may affect the probability for a student to choose a school that is located outside his or her residential area? Regression analysis is the most commonly used method to answer questions regarding relationships between variables and groups. This technique is valuable and fundamental to empirically address many educational research questions. Another example: scientists might use different amounts of fertilizer and water on different fields and see how it affects crop yield. They might fit a multiple linear regression model using fertilizer and water as the predictor variables and crop yield as the response variable. Thank you so much for listening. These were my references.